So today's video is going to be kind of an introduction to normal distributions, describing them, finding locations amongst them, and then interpreting and using that information. So let's look at percentiles first. Most of you have probably heard of a percentile because of doing, an SAT or a PSAT type test and the way they will kind of give you your score back and talk about what percentile you're at. So the percentile of a distribution is the value where the p% of the observations less than that. I think the easiest way to do this is to just look at some examples. So again, when you're looking at percentile, you're looking at not your score and lower, but what percent of the scores were lower than yours. Okay, so for example, the first one, using the scores on this first statistics test here, find the percentiles of the following students. So Norman, who earned a 72. Okay, so I think the stem plot is a little bit easier to look at because they've put them in order for you. So here's the 72 right here. So there is only one score that is less than the 72 out of 25. So Norman would be at the 4th percentile. Or 4% of the scores were lower than Norman's, right? If we do the actual math, we get this times 100, we get the 4%. So looking at Katie, who earned a 93. So Katie had the highest score on the test. Here's the 93 right here. Okay, but remember, we factor percentile by finding how many scores were below that score. So while Katie had the highest score, that does not put her at the 100th percentile because doesn't have a higher score than herself. So of the scores here, 24 out of 25 were lower than Katie's. So Katie ended up with a score at the 96th percentile. And now if we look at example C with the two students that earned a score of an 80, they earned the exact same score. So when we're looking at these scores here, we're looking at all of these scores here as being below them. So when we count those up, we find out that 12 of the 25 were below the score of an 80. And so therefore, they would be at the 48th percentile. Okay, so let's look at some graphs that we could make using percentile. So we've seen the first part of this table before. Here's our data with age, here's our frequency, and here's our relative frequency. Remember, relative frequency would be the percent. For example, this graph is looking at presidents and the age they were at their inauguration. So between the ages of 40 and 44, there were 2 presidents out of 44 when this data was collected that had been inaugurated at the age between 40 and 44. And so that would become our relative frequency of 4.5% of the presidents were inaugurated with the ages between 40 and 44. Where we can expand on this and look at this in percentile form is by then looking at cumulative frequency and cumulative relative frequency. So cumulative, right, that's going to be our total. We're adding things up, we're putting things together. So if I look at this second age bracket, the 45 to 49, I had 7 presidents that were inaugurated between ages 45 and 49. But my cumulative relative frequency is 9. So with my cumulative relative frequency, I'm looking at whatever designation I had, so 45 to 49, and anything below that. So my cumulative relative frequency is going to be the 7 presidents that were my cumulative frequency will be the 7 presidents that were inaugurated between ages 45 and 49, plus the 2 that were inaugurated between ages 40 and 44. And then when I calculate my cumulative relative frequency, now I'm taking that cumulative frequency and putting it out of 44. So what that effectively is giving me is a percentile score, or 20.5%. And I can put that into the graph. Right, you'll see my graph is labeled nicely here with my y-axis, my cumulative relative frequency, and I put my units here of percent. You notice I eventually end up at 100 because I'm going to have accounted for all 44 presidents by the time I get to the top or the highest age bracket that I have there. I'm going to have accounted for 44 out of 44 presidents. And so I'm going to end up with 100. And this would be an example here of this cumulative relative frequency graph. So when I look at these data points, for example, when I look at this data point right here, that data point is telling me that approximately 20% of our presidents were inaugurated before the age of 50, because again, it's a cumulative frequency graph here. And so we can use that information to draw some conclusions, look at trends, that kind of thing. So let's look at an example of how we could use this kind of information here. So using the graph in 2.1 was Barack Obama, who was first inaugurated at age 47, unusually young. So I can find my age 47 on my x-axis here, probably about here-ish. And if I go up to my cumulative relative frequency graph, I can see that I end up at about here, which is at about 11%. So what that says is that about 11% of presidents were younger than Barack Obama when he was inaugurated, which would mean about 89% were older when they were inaugurated. So when the question is asked here, was he unusually young? You have some evidence to support that he was pretty young for a president to be inaugurated, since only 11% of other presidents were younger than him and 89% were older than him. So another way that we could use that is estimate and interpret the 65th percentile of the distribution. So now I'm going to go the other direction on my graph. So now I was given the percentile. So if I come up here to about 65%, draw my line over, and I want to estimate and interpret. So first I'm going to do the estimating part. So if I estimate, I come down, and that gives me approximately 58 years old. So that's my estimate, okay, that the 65th percentile of the distribution is about 58 years of age. And my interpretation of that would be approximately 65% of presidents were less than 58 years of age when inaugurated. That's my interpretation part. I'm using my context and I'm explaining what that number of 58 means. Okay, so like always, pause, take a second to attempt these on your own, and then we'll come back with the answer. Okay, so looking at the first one, the multiple choice here, Mark receives a score report detailing his performance on a statewide test. On the math section, Mark earned a raw score of 39, which placed him at the 68th percentile. Okay, what that means is it does not mean that Mark did better or worse than approximately 39% of the students. His score was a 39, but he was at the 68th percentile, which means that Mark did better than about 68% of the students who took the test. Okay, so for the next one, explaining to the mother what this means about her daughter. So if we're looking at this, the online calculator determined the daughter's at the 87th percentile for weight. So what that would mean is that 87% of girls her age, of girls of the same age, so being specific there with understanding that we're not comparing her to people that are 10 years older than her or much younger. 87% of girls of the same age weigh less than her daughter. And then the same interpretation for the height. That 67% of girls of the same age are smaller, shorter than her daughter. Or you could reverse that and say that she weighs more than 87% of girls of the same age, or she is taller than 67% of girls of the same age. So here's another example using a cumulative relative frequency graph. So take a second and see if you can go ahead and answer it by yourself. Okay, so this one, it's asking what percent of calls lasted less than 30 minutes. So I'm going to go ahead and I'm going to find 30 minutes on my x-axis here. And I'm going to come up to my relative frequency. And then I'm going to go on and head over. And we'd say approximately 60% were less than 30 minutes, which would then leave approximately 40% to be greater than 30 minutes. The second part here is asking us to estimate Q1, Q3, and the IQR for the distribution. Well, if we remember, Q1 is going to represent about 25% of our data points. Q3 is going to be at about 75%. So again, using my cumulative relative frequency, I can find about 25%, which would be about here. So let's say about 12. Okay, so about 12 minutes for Q1. And Q3, if I come on up to 75%. So Q3, we'd say also about, let's say about 33 minutes, which leaves my IQR to be 33 minus 12, which will give me 21 minutes for my IQR of the distribution. Okay, and so that would be where about the middle 50% of the data points are. They're in that range of a range of 21 minutes, okay, with 12 marking Q1 and 33 marking Q3. Now let's look at how we can figure out how we can use this kind of information about percentiles and such to determine where a data point is going to fall on the curve or on the, within the data here. So we can do that by standardizing the data, calculating what we call a Z-score or a standardized score. This is one of the few formulas that is not on your formula chart. Okay, so I cannot stress this enough. This is a formula you need to get down. Again, it is not on your formula chart. So when you're calculating a Z-score to find a location on the distribution, okay, you're going to be using the data point. That's what the X is there. So the data point minus the mean over the standard deviation. So for example, this is the stem plot from before with the test scores. Okay, and this is a printout of information that was given to us below. So we know the mean. Okay, we know the standard deviation. So we could standardize these scores and figure out where they fall on the curve or within the data set. And by standardizing these curves, it tells us what that does is we convert these data points into standard deviation units. So basically what it will do is it will tell us how many standard deviations away from the mean the data point is. So let's say, for instance, they had a negative Z-score of a 1.5. So that would mean that the data point you're referring to is 1.5 standard deviations below the mean. Let's say they had a Z-score of 3. So that would mean that they are 3 standard deviations above the mean, which is really high, which would most likely be an outlier. Okay, so that's what when you standardize a score, that's what it's telling you, is how many standard deviations away from the mean they are, whether it's above or below. Okay, so let's look at what this means with these example problems here. So the first one we have here, it's Katie, who scored the 93. It has us finding the standardized score, the Z-score, and interpreting it. So Katie scoring that 93, so she'd be a 93 minus our mean of 80 divided by our standard deviation of 6.07. Again, this formula is not on your formula chart, which would give us about 2.14. Again, we're asked to interpret each value in context. So what that would mean is that Katie scored approximately 2.14 standard deviations above the mean on this particular test. Again, making sure we realize it's for this test, not a different test that Mr. Pryor gave or a different test in a whole other class, right, on this particular test that they're referring to. So looking at the second one, Norman earning the 72. So Norman would be his score minus the mean over the standard deviation, which gives us a negative value this time of negative 1.32. So what that would mean is that Norman, and I'm going to shorthand this, okay, approximately 1.32 standard deviations below the mean on this test. Okay, so let's come back to Jenny, and we're going to look at two different tests that Jenny took. And I want you to go ahead and again pause it and see if you can figure out how to approach this problem. So I don't have enough information to calculate percentiles for these tests, but I do know mean and standard deviation for both of them. Remember the Mr. Pryor statistic test, the mean was an 80 and the standard deviation was a 6.07. So what I could do is standardize both of these. So if I standardize both of these on the statistics test, this would be Jenny's Z-score, which would be a 0.99. And on the chemistry test, she earned an 82 and standard deviation of 4, which in this case gives her a Z-score of 1.5. So what this is saying is that on the statistics test, Jenny got 0.99 standard deviations above the average score. And on the chemistry test, she got 1.5 standard deviations above the average score. So what this is saying, if we distributed the scores out amongst a curve, because it said they were fairly symmetric, okay, on one of them, Jenny would be landing about here, right, if my mean is at the middle, or actually for a standardized score, that middle there, that mean would be 0. Because I'm going to go however many standard deviations above and below that. Okay, so this would be her chem score here, and this would be her stat score here. So relatively speaking, she did better on the chemistry test, even though she got a lower score than she did on the statistics test. So here's another example. Pause, try to work through it, and then we'll give you the answer. Okay, so for Lynette, if we're going to find and interpret her Z-score, she is 65 inches tall. Our mean here is 67, and our standard deviation is 4.29, which gives us a Z-score of approximately negative 0.4662. So we found her Z-score. Interpreting her Z-score, Lynette would be approximately 0.4662, and I'm going to actually erase the negative because I'm going to do it in words. 0.4662 standard deviations below the mean class height. Okay, so let's look at the information here about Brent. Brent is 74 inches tall. How tall is Brent compared with the rest of the class? Give appropriate numerical evidence to support your answer. Well, if we look at this, Brent is 74 inches tall, so he is right here. We know we have a sample size of 25. So including Brent, there are only 2 more people taller than him. So we could find his percentile. Brent is 22 out of 25, or 22 people are shorter than Brent. Okay, so that would put him at about the 88th percentile, meaning that he is taller than 88% of his class. And that would allow you to do a comparison with the rest of his class. You can also find his Z-score being 1.632. And so you could also state that he is approximately 1.632 standard deviations above the average height. But again, if I'm comparing it to the rest of the class, okay, stating that he's at the 88th percentile and showing my work to get there might be the better way to go here. Okay, and the last one for Brent here regarding the basketball team, this is just an algebra equation, right? We know that his z-score is negative 0.85. We know that z-score is calculated by taking the data point, which is his 74 inches, minus the mean, which in this case is 76 inches of the basketball team, the mean of the 8 players on the basketball team, and it wants to know the standard deviation. So now I just algebraically need to solve for standard deviation, which gives me a standard deviation of approximately 2.353. So occasionally we'll need to do what's called transforming data. So when we transform data, we can basically, we're manipulating the entire data set by a constant, whether that's adding a constant, subtracting a constant, multiplying, dividing by a constant. An easy example would be, for instance, let's say we had a bunch of data measured in Fahrenheit in class, in a science class. Well, in science class, we use Celsius for temperature. So maybe we need to transform that whole data set into a Celsius measurement instead of a Fahrenheit. So then we would be manipulating that data set by the same constants all the way through. So what we need to be able to realize is what happens to the distribution of the data set when we manipulate it by a constant. So looking at this particular data set, so this big data set here was a set of students in Australia estimating the width of their classroom. Okay? And based off of that, based off of the guesses, okay, they went through, and here's the summary as well as the dot plot from that data. So what they did is they then went through and determined the error that was made in the guessing of this data set and transformed by the error. And by doing that, what they did is they subtracted 13 from everything. So when you are adding or subtracting a constant, what you need to realize is that the center is going to change. So our measures of center and location, so for instance, mean, median, quartiles, percentiles, those will all change. But the overall shape and spread stays the same. It will not change. I think it's easiest to see if we look at the dot plot here. So on the bottom there are the guesses, and on the top here are the errors, right? And then on the bottom here are the guesses. And if you look, the shape and the spread is exactly the same, right? They have the same shape here, and they have the same spread. What they don't have is the same measures of center, because the whole dot plot has been shifted down by 13. So the measures of center are going to be different, which will change the mean, the median, the location of Q1 and Q3. But the spread, for instance, the IQR, that's still the same, the distance between them, because our shape did not change. So when we add or subtract a constant to the data set, we need to realize that center and measurements of location are going to change, but spread and shape will stay exactly the same. When we multiply or divide by a constant, now we're going to see changes in almost everything. Okay? So if we multiply or divide by a constant, center and location is also going to change. It's going to change by whatever you multiplied or divided by. Same with when we add or subtract. Let's in that last example with the error with the classroom, and we were subtracting 13 from everything. Well, the mean would be 13 less, right? So it changes by what we add or subtract. Same with multiplication. When we multiply or divide, it's also going to change our spread, but the shape stays the same. So the overall shape is going to always stay the same. It's never going to change no matter what you do. Okay. Measures of center and location are always going to change by whatever the constant was, and then spread only changes when we multiply and divide. Again, if we look at the errors here and look at what we've done here, so what has happened here is we've multiplied by about 3.28, which is why we now see the spread having gotten larger. The overall shape, though, is still the same, right? It just got fatter. So the spread got bigger, but the overall shape did stay the same. And then our measurements of location are going to change. Okay, so let's look at part A here, asking us to find the mean temperature in degrees Fahrenheit. And does the thermostat setting seem accurate? So mean is a form of location center. So remember, both location and center, our conversion here multiplies by a constant as well as adds a constant. Location and center are both affected by multiplication, division, as well as addition, subtraction. So for this one, we're given a mean of 8.4 degrees Celsius. So I need to apply both the multiplication constant as well as the addition constant to find the new mean. Which is approximately 47 degrees Fahrenheit. And the second part of the question asking us, does it seem accurate? Well, the thermostat is set at 50 degrees Fahrenheit, and the average is 47 degrees Fahrenheit. So no, it is not very accurate here. Looking at part B, it's asking us to calculate standard deviation and interpret it in context. Well, standard deviation, remember, is a form of spread. Spread is only affected by division and multiplication. So when I'm applying my constants here to standard deviation, conversion of temperature, I'm only going to apply the multiplication part, because remember, addition and subtraction don't impact spread. They remain the same. So I'm only going to apply the multiplication part, which gives us variation of approximately 4 degrees Fahrenheit. So when I interpret this in context, our typical data point is approximately 4 degrees Fahrenheit away from the mean of 47 degrees Fahrenheit. And the last question here is asking us about percentile. Okay, percentile, it tells us the 93rd percentile of the temperature readings is at 12 degrees Celsius. What is the 93rd percentile temperature in Fahrenheit? Well, again, percentile is a form of location. Therefore, both the multiplication and the addition constants are going to impact this. So I'm going to apply both of them to determine our 93rd percentile. Case is approximately 53.6 degrees Fahrenheit. So let's take a second and put these two things together, our transformations as well as our z-scores. So if we are transforming an entire data set, we can what we call standardize that set. And when we standardize that set, we end up with a mean of 0 and a standard deviation of 1, which will be helpful to us when we go do some other conversions and calculations and such later. Okay, so for example, if you look at the test scores here, right, our mean for that first statistics test was an 80, I believe. Yeah, there's our mean right there, was an 80. Okay, and when we transform that whole data set, taking it down to, if we look at how we calculate our z-score, right, minus the mean over the standard deviation, right? So if we subtract the mean, okay, we get down to a mean of 0, right? 80 minus 80. So we get down to a mean of 0. And so that moves our location down. And when we divide the standard deviation, it brings us down to a standard deviation of 1, because we're standard deviation divided by standard deviation. So basically, this curve right here, this one right here, this dot plot is showing you all the z-scores. So we calculated the z-score for all 25 tests, meaning that we subtracted the mean and divided by the standard deviation. And so you'll notice it changes our locations, and our measurements of center change. Okay, and then the overall shape stays the same. Okay, as well as the spread is going to shift a little bit, because our spread now, instead of, well, it's not affected by the subtraction, our spread is affected by the division. So you'll notice now we're on a scale of 1 as opposed to on the scale of 5. So our spread will change. So let's look at some application for this. Again, pause, see if you can do it yourself, and then we'll check the answer. Okay, so to do this, we need to be thinking about what kind of conversion is happening here, right? So if I'm converting from inches to centimeters, there are 2.54 centimeters in each inch. So this is a multiplication here. So basically, I'm going to take every data point here and I'm going to multiply it by 2.54. So what that will do for our center, it's going to increase our center. It's going to multiply the center by 2.54. So we have a mean here of 67. So it's going to alter our center by 67 times 2.54, which is 170.18. Okay, if we look at our shape, remember, shape isn't affected by either one, so our shape would end up staying the same. It's not affected by adding, subtracting, or dividing, multiplying by a constant. Okay, and then our spread is affected by multiplication and division. When we multiply, it's going to actually increase the spread because I'm going to multiply my standard deviation of 4.29 times 2.54. I'm going to apply that constant and I'm going to get a new spread of 10.8966 centimeters. So that would be how it's going to impact it. Okay, so take a look at this one and we'll go through it. So again, focusing on our distribution here. So in this case, if you need to, maybe draw yourself a little picture, right? She had the students stand on this platform. So, and they measured from the top of their head all the way down to the ground. So basically every measurement is inflated by 6 inches. So what it's asking here is how would the shape, center, and spread of this distribution compare with the original height distribution? So essentially what I've done is I've added 6 inches to everything. So my measurements of location and center, they're going to be affected. I'm going to be adding 6 inches to my mean here. So my mean will shift over to 73 inches. Basically, my entire dot plot is going to shift to the right 6 inches because my measurement of spread is not affected by the 6 inch, by adding a 6 inch constant, and neither is my shape. Remember, my shape stays the same regardless of addition, subtraction, or multiplication, division. Okay, so now I'm going to convert all of them into z-scores. And again, how would that affect shape, center, and spread of the distribution? Well, again, remember to convert into a z-score. We are taking the data point minus the mean divided by the standard deviation. Okay, so what will happen is my center is going to shift. My center is going to become 0 if I take the z-scores of everything. I'm going to standardize my dot plot and my center is going to move over to 0 because I've subtracted. Again, I did a subtraction constant to everything and I did a division constant to everything. So my center is going to move down to 0. My center is going to decrease. My shape is going to stay the same because it always stays the same. And my spread should decrease because again, I divided by standard deviation. So my spread, I can't spell, should go down. And again, my spread, my standard deviation is going to become 1. I end up with a standardized curve that has a mean centered at 0 and a standard deviation of 1. So I get that curve if I take the z-score, if I make a plot of the z-score of every single data point in our set. So that's what would happen to that. So we'll look at lots of examples. We'll work with this because we really need to get a handle on this and be very comfortable with this as we move into more calculations using these items.